What makes reinforcement learning training so slow? Imagine teaching a robot to walk or a game-playing agent to master a complex game. It sounds simple, but the process can take a lot of time. That's because reinforcement learning training is often slow. Let's explore why that is. Reinforcement learning involves an agent learning by trying different actions in an environment. It gets rewards or penalties based on what it does. The agent needs to try many actions over many episodes to figure out what works best. This trial and error process takes a lot of time because the agent must explore a wide range of possibilities. One big reason for slow training is sample inefficiency. Unlike other machine learning methods that learn from labeled data, reinforcement learning needs millions of interactions with the environment. For example, training a robot to walk might requiring hundreds of thousands of steps. Each step involves the robot moving, sensing, and receiving feedback, which takes time. Another factor is the complexity of the environment. If the environment is complicated, like a physics simulation or a real-world scenario, each interaction can be slow. Running detailed simulations or processing real-time data adds to the time needed for each training step. Experience replay is also a factor. Many reinforcement learning algorithms store past interactions in a buffer. They reuse these experiences to learn better. But managing this buffer and sampling from it can slow down training, especially as it grows larger. Logging and visualization are helpful for tracking progress, but they can also slow things down. Updating graphs and metrics during training uses resources and can add delays, especially during long training sessions. Deep neural networks are often part of reinforcement learning. Training these networks involves complex calculations called gradient computations. These are computationally intensive and requiring powerful hardware. If the implementation isn't optimized, training can take even longer. Parallelization can speed things up, but not all reinforcement learning algorithms are designed for it. Some are sequential and need to wait for each step to finish before moving on. This limits the ability to use multiple processors or graphics processing units effectively. To make reinforcement learning faster, researchers try to reduce unnecessary logging, optimize memory use, and use parallel computing when possible. Simplifying the environment or the state space can also help. Understanding these factors is important because slow training means higher computational costs and more energy use. This raises concerns about sustainability and efficiency in artificial intelligence development. In summary, reinforcement learning training is slow because it requires extensive exploration, complex environment interactions, heavy neural network calculations, and managing large amounts of data. Addressing these challenges helps make reinforcement learning more practical and accessible for real-world applications.